In this session, we consider second-order homogeneous differential equations. A y2 prime plus b y prime plus cy equals 0. Then, as I said, we can substitute y equal exponential mx into the equations. Y prime equal m exponential mx. y2 prime equal m square exponential mx. So it becomes equal to the am square plus bm plus c times exponential mx. Exponential mx cannot become 0, so we can divide it by exponential mx in the both sides of the equations. It becomes am square plus bm plus c equals 0. The solution is expressed m equal minus b plus minus square root b square minus 4ac over 2a. So there are three forms of the solutions. First case is a distinct real root. In that case, the b square minus 4ac is a positive quantity. M becomes real root. When the b square minus 4ac equals 0, in this case the m is expressed minus b over 2a. We have only single solutions. Repeated real root. Last case is a b square minus 4ac is a negative quantities. In this case, solution becomes a complex root. So we consider the distinct real root first case. So we have two solutions. First one is m sub 1 is minus b plus square root b square minus 4ac over 2a. M sub 2 is took a negative quantities. So minus b minus square root b square minus 4ac over 2a. So in this case, general solution is given by the sum of the two solutions of the exponential m sub 1x, exponential m sub 2x, and the constant quantity of the c sub 1 and c sub 2. So general solution is expressed y equals c sub 1 exponential m sub 1x plus c sub 2 times exponential m sub 2x. C sub 1 and c sub 2 correspond to the integration constant. So I'd like to show you the different methods to find the general solutions. So this is am squared plus bm plus c equals 0. So by dividing by a in the both sides, this is m squared plus b over am plus c over a equals 0. Then solutions of this equation is m sub 1 and m sub 2. This equation have to be expressed m minus m sub 1, m minus m sub 2 have to be equal 0. This equation is m squared minus m sub 1 plus m sub 2 m plus m sub 1 m sub 2 equals 0. So b over a correspond to the minus m sub 1 plus m sub 2. C over a corresponds to the product of the m sub 1 times m sub 2. Equation is expressed y2 prime minus m sub 1 plus m sub 2 y prime plus m sub 1 m sub 2 equals 0. So if we use a differential operator of capital D, is d minus m sub 1 capital D minus m sub 2 y equals 0. We can multiply the exponential minus m sub 1 x in the both sides. So d minus m sub 1 d minus m sub 2 y equals 0. Right hand side is 0 times exponential minus m sub 1 x becomes 0. We could consider these ones. As I explained, exponential minus m sub 1 x times capital D minus m sub 1 is expressed d exponential minus m sub 1 x d minus m sub 2 y equals 0. So we can switch the term of the capital D and exponential m sub 1x. So we combine the two terms into the single terms, like integrating factors. Then derivative of this quantity is 0. So this quantity exponential minus m sub 1x times d minus m sub 2y have to be the constant quantity c sub 0. This is constant. So we can express this equation is a d minus m sub 2 y equals c sub 0 exponential positive m sub 1x by multiplying the exponential m sub 1x in the both sides of the equations. Then we multiply the exponential minus m sub 2x in the both sides. Then d minus m sub 2y equals c sub 0 exponential m sub 1 minus m sub 2x. Again, we could consider this. Change the term of the capital D and the exponential functions. So we combine the two terms into the single terms. This is d exponential minus m sub 2xy equals c sub 0 exponential m sub 1 minus m sub 2x. Then we could integrate in the both sides of the equations. Exponential minus m sub 2x y integrating over this quantity is a c sub 0 over m sub 1 minus m sub 2 exponential m sub 1 minus m sub 2x plus integration constant. Then this c sub 0 over m sub 1 minus m sub 2 is a constant quantities. We rename it c sub 1. Then by multiplying the exponential m sub 2x in the both sides of the equation, we have a general solution of the y. C sub 1 exponential m sub 1x plus c sub 2 exponential m sub 2x. This is a general solution whether we have a distinct real root. Okay, this solution, general solution, is exactly same with this solution. So you can use either method to find the solutions of a second order homogeneous differential equations when you have two distinct real roots. Okay, this is the end of this lecture.